Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The measurement of time, in its most fundamental and unhurried sense, has occupied the attention of human civilizations for a span of roughly 5,000 years, and perhaps considerably longer than that, depending upon how one chooses to define the act of measurement itself. The earliest efforts to quantify the passage of hours and days were, it must be noted, remarkably imprecise by modern standards, yet they represented a profound intellectual achievement for the societies that developed them. The very concept that time could be divided into discrete, repeatable units was not at all obvious to early peoples, and the gradual realization that such division was both possible and useful unfolded over many centuries of patient observation and quiet experimentation. The sun, as one might expect, served as the first and most readily available timekeeper for ancient peoples across nearly every inhabited region of the world. The shadow cast by a vertical stick or stone, known in later terminology as a gnomon, moved in a predictable arc from west to east as the sun traversed the sky from its rising in the east to its setting in the west. This simple observation, repeated day after day and season after season, formed the basis of what would eventually become the sundial, one of the oldest known timekeeping instruments in the historical record. The earliest known sundials date to approximately 1500 BCE in Egypt, though it is entirely plausible that cruder versions existed for many centuries before that date, their evidence having been lost to the slow and indifferent processes of decay and burial. The Egyptian sundial, in its most basic form, consisted of a flat base with a raised crossbar at one end. The shadow of the crossbar fell upon the base, which was marked with lines indicating the passage of hours. It should be noted that these hours were not of equal length, as they divided the period of daylight into 12 equal parts, regardless of the season. In summer, when the days were long, each hour was correspondingly longer, and in winter, when the days were short, each hour contracted. This system of temporal hours, as they are sometimes called, persisted in various parts of the world for well over 2,000 years. And it was not until the widespread adoption of mechanical clocks in the 14th century that the concept of equal hours became standard. The Egyptians were not alone in their early experiments with solar timekeeping. The Babylonians, whose civilization flourished in the fertile plains between the Tigris and Euphrates rivers in what is now modern Iraq, developed their own sophisticated system of time measurement. The Babylonian contribution to timekeeping was, in many respects, more lasting than that of the Egyptians, for it was the Babylonians who established the sexagesimal system of counting, based on the number 60, which still underlies our modern division of the hour into 60 minutes and the minute into 60 seconds. The reasons for the Babylonian preference for base 60 are not entirely certain, but it is commonly suggested that 60 was chosen because it is divisible by a large number of smaller integers, specifically by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60 itself, making it exceptionally convenient for the purposes of fractional calculation. The water clock, known by its Greek name clepsydra, meaning literally water thief, represents another significant chapter in the long and methodical history of timekeeping. Water clocks operated on the principle that water flowing through a small aperture at a controlled rate could serve as a measure of elapsed time. The simplest form of water clock consisted of a vessel with a small hole near the bottom, from which water dripped steadily into a receiving container. As the water level in the upper vessel fell, markings on its interior wall indicated the passage of time. Alternatively, in the receiving type of water clock, the rising water level in the lower container served the same purpose. The earliest known water clocks date to approximately 1500 BCE in Egypt, roughly contemporaneous with the earliest sundials. A fragment of a stone water clock was discovered in the Temple of Ammonius at Karnak, dating to the reign of Amenhotep III, who ruled from approximately 1391 to 1353 BC. This particular clock was designed as an outflow device, with 12 columns of markings on its interior surface corresponding to the 12 months of the Egyptian calendar. The varying depths of the markings accounted for the different lengths of night throughout the year, a rather elegant solution to the problem of seasonal variation in the hours of darkness. Water clocks were adopted and refined by numerous civilizations over the following millennia. The Greeks made significant improvements to the basic design, most notably through the work of Ctesibius of Alexandria, who lived during the 3rd century BC. Ctesibius is credited with developing what might be called the first precision water clock, which incorporated a float mechanism connected to a pointer that indicated the time on a graduated scale. His design also included an overflow device that maintained a constant water level in the upper reservoir, thereby ensuring a more consistent flow rate and, consequently, a more accurate measurement of time. The improvement in accuracy achieved by this relatively simple modification was quite substantial, reducing the typical error from perhaps 30 minutes per day to approximately 15 minutes per day. The Romans, who were nothing if not practical in their adoption and adaptation of technologies from conquered peoples, made extensive use of water clocks in both public and private settings. Roman courts used water clocks to limit the length of speeches, a practice that gave rise to the Latin phrase aquam dare, meaning to give water, which signified the granting of time for a speaker to present his case. The amount of water allocated to each speaker was carefully measured, and when the water ran out, the speaker was required to conclude his remarks, regardless of whether he had finished making his point. This practice, mundane as it may seem, represents one of the earliest known instances of time being used as a formal mechanism of social regulation. In China, the development of water clocks proceeded along a somewhat different trajectory, reaching a level of mechanical sophistication that was not matched in Europe for several centuries. The Chinese polymath Su Song, who lived from 1020 to 1101 CE, constructed an elaborate water-powered astronomical clock tower in the city of Kaifeng in the year 1088. This remarkable device, which stood approximately 12 meters tall, incorporated a water-driven escapement mechanism that regulated the turning of an armillary sphere and a celestial globe. The clock tower also featured a series of mechanical figures that emerged from doors at regular intervals to announce the time by holding up placards, ringing bells, and striking drums. Susong's clock tower operated for approximately 30 years before it was disassembled following the fall of Kaifeng to invading forces in 1127. The hourglass, another ancient timekeeping device, operated on a principle similar to that of the water clock, but substituted sand for water as the flowing medium. The exact origins of the hourglass are somewhat obscure, and there is considerable scholarly debate regarding when and where it was first developed. Some historians have suggested that hourglasses were used in ancient Greece or Rome, but the earliest unambiguous evidence for their existence dates to the 8th century CE in Europe. A fresco in the cathedral at Chartres, dating to approximately 1338, depicts an hourglass, and by the 14th century, hourglasses were in widespread use throughout Europe, particularly in maritime navigation and in churches, where they were used to time sermons. The sand used in hourglasses was not, as one might assume, ordinary beach sand. Suitable sand had to possess several specific properties in order to flow smoothly and consistently through the narrow waist of the glass. The grains needed to be of uniform size, typically between 0.1 and 0.3 millimeters in diameter, rounded in shape rather than angular, and free from moisture. Marble dust, powdered eggshell, and finely ground tin were all used at various times as alternatives to natural sand, each offering its own particular advantages in terms of flow characteristics and durability. The mechanical clock, which would eventually revolutionize the measurement of time and fundamentally alter the rhythms of daily life across much of the world, emerged in Europe during the late 13th century. The precise origins of the mechanical clock are, like those of many significant inventions, somewhat difficult to pin down with certainty. No single inventor can be credited with its creation, and the development of the key mechanism, the escapement, appears to have occurred gradually through the contributions of multiple individuals working in different locations over a period of several decades. The escapement is the component of a mechanical clock that converts the continuous rotational force provided by a falling weight or a coiled spring into the discrete, regular back and forth motion that drives the clock's hands. The earliest form of escapement, known as the verge escapement, consisted of a vertical shaft, called the verge, fitted with two small plates, called pallets, that engaged alternately with the teeth of a crown wheel. As the crown wheel turned under the influence of the driving weight, the pallets caught and released the teeth in a rhythmic pattern, producing the characteristic tick-tock sound that would become so closely associated with clocks in the centuries to follow. The earliest references to mechanical clocks in European records date to the period between 1280 and 1320. A reference in the Annals of Dunstable Priory in England, dated to 1283, mentions the installation of a clock, and the cathedral at Exeter is known to have had a clock by 1284. These early clocks were large, cumbersome devices installed in church towers and public buildings, and they typically had no dials or hands. Instead, they announced the time by striking bells, the word clock itself being derived from the medieval Latin clocca, meaning bell. The accuracy of these early mechanical clocks was, by modern standards, quite poor, with errors of approximately 15 to 30 minutes per day being common. The development of the mechanical clock had profound social and economic consequences that extended far beyond the mere measurement of time. Prior to the introduction of clocks, the rhythm of daily life in medieval Europe was governed primarily by the natural cycles of daylight and darkness, and by the canonical hours of the Church, which divided the day into periods of prayer. The mechanical clock introduced an abstract, uniform measure of time that was independent of both the sun and the Church, and this new measure gradually came to regulate an ever-expanding range of human activities, from the hours of labor to the scheduling of meals and the timing of public events. The 14th and 15th centuries witnessed a gradual but steady improvement in the accuracy and reliability of mechanical clocks, driven in large part by the increasing demand for precise timekeeping in commerce, navigation, and administration. The verge escapement, which had served as the standard mechanism for the earliest tower clocks, was inherently limited in its accuracy because the rate at which the verge oscillated was sensitive to variations in the driving force applied by the falling weight. As the weight descended and the force on the crown wheel changed, the oscillation rate varied accordingly, introducing errors that accumulated over the course of a day. One significant development during this period was the introduction of the fusee, a cone-shaped pulley that was designed to equalize the force transmitted from the mainspring to the clock mechanism. The mainspring, a coiled strip of metal that stored energy when wound and released it gradually as it unwound, had been introduced as an alternative to hanging weights in the early 15th century. However, a mainspring delivers a greater force when fully wound than when nearly unwound, and this variation in force caused the clock to run faster when freshly wound and slower as the spring ran down. The fusee compensated for this variation by means of a carefully calculated conical shape that allowed the chain or cord connecting the mainspring barrel to the fusee to exert a constant torque on the clock mechanism regardless of the state of the spring. The mathematical relationship between the shape of the fusee and the characteristics of the mainspring was a matter of considerable interest to clockmakers and mathematicians alike, and the design of optimal fusee profiles remained an active area of investigation well into the 19th century. The introduction of the mainspring also made it possible, for the first time, to construct clocks that were small enough to be carried on the person. The earliest portable timepieces, which appeared in the late 15th and early 16th centuries, were not called watches, but rather clock watches or simply small clocks. They were typically housed in cylindrical or drum-shaped cases made of brass or gilded bronze, and they were worn around the neck on a chain or attached to the belt. The accuracy of these early portable timepieces was extremely poor, often losing or gaining as much as several hours per day, and they were regarded more as novelties and status symbols than as practical instruments for telling time. Peter Henlein of Nuremberg, who was active in the early 16th century, is often credited with the invention of the first watch, though this attribution has been questioned by some historians. What is more certain is that Nuremberg was an important center of clockmaking during this period, and that the city's skilled metalworkers and instrument makers contributed significantly to the miniaturization of clock mechanisms. The so-called Nuremberg eggs, a term that was long believed to refer to egg-shaped watches, but which may in fact derive from a misreading of the German word Erlien, meaning small clock, were among the earliest portable timepieces to achieve widespread recognition. The next truly transformative development in the history of timekeeping came in 1656, when the Dutch mathematician and physicist Christian Huygens invented the pendulum clock. The pendulum, a weight suspended from a fixed point by a string or rod, had been studied extensively by Galileo Galilei in the late 16th century. Galileo had observed that a pendulum of a given length swings back and forth with a nearly constant period regardless of the amplitude of its swing, a property known as isochronism. He recognized that this property made the pendulum ideally suited for use as a timekeeper, and he even sketched designs for a pendulum clock, but he did not live to construct one. Huygens succeeded where Galileo had not, constructing a working pendulum clock and obtaining a patent for his design from the States General of the Netherlands on June 16, 1657. The key innovation in Huygens's design was the combination of a pendulum with an escapement mechanism that both sustained the pendulum's oscillation and counted its swings. The resulting clock was dramatically more accurate than any previous timekeeper, with errors of approximately 10 seconds per day compared to the 15 to 30 minutes per day typical of verge escapement clocks. This represented an improvement in accuracy of roughly 2 orders of magnitude, one of the most significant single advances in the entire history of timekeeping. Huygens continued to refine his pendulum clock over the following years, and in 1673 he published his masterwork, Horologium Oscillatorium, which contained a thorough mathematical analysis of pendulum motion. In this work, Huygens demonstrated that a simple pendulum is not, in fact, perfectly isochronous. The period of a simple pendulum depends slightly on the amplitude of its swing, a relationship that introduces a small but measurable error into the timekeeping of a pendulum clock. Huygens showed that perfect isochronism could be achieved if the pendulum bob were constrained to follow a cycloidal path rather than a circular arc, and he designed curved cheeks for the pendulum suspension that would guide the bob along the required cycloid. This mathematical insight, while of considerable theoretical elegance, proved to be of limited practical value, as the friction introduced by the cheeks tended to offset the improvement in isochronism. The pendulum clock reached its highest level of refinement in the hands of English clockmakers during the late 17th and 18th centuries. Thomas Tompion, who was born in 1639 and died in 1713, is widely regarded as the father of English clockmaking. Tompion produced clocks of extraordinary quality and precision, and his workshop in London set standards of craftsmanship that influenced clockmakers throughout Europe. His pupil and successor George Graham, who lived from 1673 to 1751, made further important contributions, including the invention of the deadbeat escapement in approximately 1715. The deadbeat escapement, unlike the earlier anchor escapement, did not cause the pendulum to recoil slightly at each beat, a characteristic that improved the consistency of the pendulum's swing and thereby enhanced the accuracy of the clock. Graham also invented the mercury pendulum, a device designed to compensate for the effects of temperature on the length of the pendulum rod. The period of a pendulum is determined by its effective length, which is the distance from the point of suspension to the center of mass of the bob. When the temperature rises, the pendulum rod expands, increasing the effective length and causing the clock to run slow. Graham's mercury pendulum used a glass jar filled with mercury as the bob. When the temperature rose and the rod expanded downward, the mercury in the jar expanded upward, partially compensating for the change in effective length. The degree of compensation could be adjusted by varying the amount of mercury in the jar. John Harrison, who will be discussed at greater length in connection with the problem of longitude, devised an alternative approach using a gridiron pendulum, which consisted of alternating rods of brass and steel arranged so that the thermal expansion of the brass rods offset the thermal expansion of the steel rods. The problem of determining longitude at sea was one of the most pressing scientific and practical challenges of the 17th and 18th centuries. While latitude could be determined relatively straightforwardly by measuring the altitude of the sun or of known stars above the horizon, longitude presented a far more difficult problem. In principle, longitude could be determined by comparing local time, as indicated by the position of the sun, with the time at a known reference meridian. If a navigator knew that it was noon at his current position and that it was, say, 3 o'clock in the afternoon at the reference meridian, he could calculate that he was 3 hours of longitude, or 45 degrees, to the west of the reference point. The difficulty lay in knowing the time at the reference meridian, for this required a clock that could maintain accurate time over weeks or months of travel on the pitching, rolling deck of a ship at sea. The British Parliament, recognizing the importance of the longitude problem for the safety and efficiency of maritime commerce, passed the Longitude Act of 1714, which established a board of longitude and offered prizes of up to £20,000 for a practical method of determining longitude at sea. The largest prize was reserved for a method accurate to within half a degree of longitude, which corresponded to a timekeeping error of no more than approximately 2 minutes over the course of a voyage from England to the West Indies, a journey of approximately 6 weeks. John Harrison, a self-taught carpenter and clockmaker from Barrow-upon-Humber in Lincolnshire, devoted more than 30 years of his life to the construction of a series of increasingly refined marine chronometers, designated H1 through H5, that would eventually solve the longitude problem. Harrison's first marine timekeeper, H1, was completed in 1735 after 5 years of work. It was a large and complex device, weighing approximately 34 kilograms and incorporating a number of innovative features, including a pair of linked balance mechanisms that were designed to compensate for the motion of the ship. H1 was tested on a voyage to Lisbon in 1736, during which it performed well enough to earn Harrison a grant from the Board of Longitude to continue his work. Harrison spent the next 17 years constructing H2 and then H3, each incorporating improvements over its predecessor. H3, which was completed in 1757, introduced the bimetallic strip as a temperature compensation device, an invention that would find applications far beyond clockmaking. However, Harrison ultimately concluded that the approach he had taken with H1 through H3, which relied on large, complex balance mechanisms, was not the most promising path forward. In a remarkable change of direction, he began work on a much smaller timekeeper, H4, which was essentially a large pocket watch, measuring only 13 centimeters in diameter. H4, completed in 1759, proved to be a masterpiece of precision engineering. On its first official trial voyage to Jamaica in 1761 to 1762, it lost only 5.1 seconds over a period of 81 days, far exceeding the accuracy requirements of the Longitude Act. Despite this remarkable performance, Harrison faced considerable opposition from some members of the Board of Longitude, particularly the Astronomer Royal Neville Maskelyne, who favored an alternative astronomical method of determining longitude known as the method of lunar distances. Harrison did not receive the full prize until 1773, when he was 79 years old, and only after the personal intervention of King George III. The development of the marine chronometer had implications that extended well beyond the immediate problem of navigation. The techniques of precision engineering that Harrison and his successors developed, including temperature compensation, anti-friction devices, and improved escapement mechanisms, contributed to the broader advancement of precision manufacturing and metrology. The marine chronometer also established the principle that time could serve as a universal coordinate, linking the measurement of time to the measurement of space in a manner that would prove fundamental to both navigation and, eventually, to the theory of relativity. The 19th century brought about a series of developments in timekeeping that were intimately connected with the expansion of the railway network across Europe and North America. Prior to the railway age, each town and city kept its own local time, determined by the position of the sun at its particular longitude. The difference in local time between two places was proportional to their difference in longitude, with each degree of longitude corresponding to a time difference of 4 minutes. Thus, the local time in Bristol, which lies approximately 2.6 degrees west of London, was roughly 10 minutes behind London time. This variation in local time posed few difficulties in an era when the fastest means of travel was the horse, but the coming of the railway, with its fixed schedules and relatively high speeds, made the patchwork of local times increasingly problematic. The dangers of operating a railway system without a uniform time standard were graphically illustrated by a number of accidents and near misses in the early years of rail transport. If a train departed from one station at a time set by the local clock and was expected to arrive at another station at a time set by a different local clock, the potential for confusion and collision was obvious. The Great Western Railway in England was among the first to adopt a uniform time standard, switching to London time, also known as Greenwich Mean Time, in November 1840. Other railway companies followed suit over the next few years, and by 1855, the vast majority of public clocks in Britain had been set to Greenwich Mean Time. Though the legal adoption of GMT as the standard time for all of Britain did not occur until the passage of the Statutes, Definition of Time, Act in 1880. The situation in the United States was considerably more complex, owing to the vast east-west extent of the country. In the early 1880s, there were approximately 300 local times in use across the United States, and the railway companies themselves maintained some 53 different time standards. The confusion was addressed on November 18, 1883, a date that became known as the Day of Two Noons, when the major railway companies adopted a system of 4 standard time zones: Eastern, Central, Mountain, and Pacific, each separated by exactly 1 hour. This system was not given the force of law until the passage of the Standard Time Act in 1918, but it was widely adopted by cities and businesses almost immediately upon its introduction. The international standardization of time zones was formalized at the International Meridian Conference held in Washington, D.C. in October 1884. 25 nations sent delegates to this conference, which resolved, among other things, that the prime meridian, the line of zero longitude from which all other longitudes would be measured, should pass through the center of the transit instrument at the Royal Observatory in Greenwich, England. The conference also recommended the adoption of a universal day beginning at midnight at the prime meridian, and the establishment of a system of time zones based on 15-degree intervals of longitude, each zone differing from the next by exactly 1 hour. Not all nations immediately adopted these recommendations, and some, such as France, held out for many years before accepting the Greenwich meridian, France having previously used the Paris meridian as its own prime reference. The quest for ever greater accuracy in timekeeping took a dramatic new direction in the 20th century with the development of electronic and atomic clocks. The first significant step in this direction was the invention of the quartz crystal oscillator, which exploited the piezoelectric properties of quartz to generate extremely stable electrical oscillations. The piezoelectric effect, discovered by Jacques and Pierre Curie in 1880, is the phenomenon whereby certain crystalline materials generate an electrical voltage when subjected to mechanical stress and, conversely, undergo a slight mechanical deformation when an electrical voltage is applied to them. A thin slice of quartz crystal, cut to the appropriate dimensions, will vibrate at a natural resonant frequency when stimulated by an alternating electrical signal. And this frequency is determined primarily by the physical dimensions of the crystal and is remarkably stable over time. The first quartz clock was constructed by Warren Marison and J. W. Horton at Bell Telephone Laboratories in the United States in 1927. Their clock used a quartz crystal vibrating at a frequency of approximately 50,000 Hz, and it achieved an accuracy of better than 1 second per year, a performance that was approximately 1,000 times better than the best mechanical pendulum clocks of the era. The quartz clock rapidly became the standard for precision timekeeping in scientific and technical applications, and by the 1940s, quartz clocks at national standards laboratories around the world were serving as the primary references for the maintenance and dissemination of accurate time. The development of the quartz wristwatch in the late 1960s brought the benefits of quartz timekeeping to the general public. The first commercially available quartz wristwatch, the Seiko Astron 35 SQ, was released on December 25, 1969, at a price of 450,000 Japanese yen, which was at that time roughly equivalent to the cost of a small car. The Astron used a quartz crystal vibrating at 8,192 Hz, and it achieved an accuracy of approximately plus or minus 5 seconds per month, far superior to any mechanical watch. The high initial price of quartz watches fell rapidly over the following years as manufacturing techniques improved and economies of scale were achieved, and by the late 1970s, inexpensive quartz watches had become widely available, precipitating a crisis in the traditional Swiss mechanical watch industry that became known as the Quartz Crisis, or, in French, La Crise du Quartz. The atomic clock, which represents the current pinnacle of timekeeping technology, operates on a fundamentally different principle from all previous timekeeping devices. Rather than relying on the mechanical oscillation of a pendulum, the vibration of a quartz crystal, or the flow of water through an aperture, the atomic clock measures time by counting the oscillations of electromagnetic radiation associated with a specific quantum mechanical transition in an atom. The idea that atomic transitions could serve as a basis for timekeeping was first suggested by the American physicist Isidore Rabi in 1945, drawing on his earlier work on molecular beam magnetic resonance, for which he had received the Nobel Prize in Physics in 1944. The first operational atomic clock was built by Harold Lyons at the National Bureau of Standards in the United States in 1949. This clock used the vibration of ammonia molecules as its frequency reference, but it proved to be less accurate than the best quartz clocks of the time. A more successful approach was taken by Louis Essen and Jack Perry at the National Physical Laboratory in Teddington, England, who constructed the first practical cesium beam atomic clock in 1955. Their clock used the frequency of the microwave radiation emitted by cesium, 133 atoms undergoing a particular hyperfine transition, as its reference frequency. This frequency, which was measured with great care and found to be exactly 9,192,631,770 cycles per second, would eventually become the basis for the international definition of the second. In 1967, the 13th General Conference on Weights and Measures formally redefined the second, which had previously been defined as a fraction of the mean solar day, in terms of the cesium 133 hyperfine transition. The new definition stated that 1 second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium 133 atom. This redefinition marked a fundamental shift in the conceptual basis of timekeeping, severing the link between the measurement of time and the rotation of the Earth that had existed since the earliest days of human civilization. The accuracy of cesium atomic clocks has improved enormously since the first models of the 1950s. The best cesium fountain clocks currently in operation, such as NIST F2 at the National Institute of Standards and Technology in Boulder, Colorado, achieve an accuracy of approximately 1 second in 300 million years. This extraordinary precision is achieved by cooling cesium atoms to temperatures very close to absolute zero using laser cooling techniques, thereby reducing the thermal motion of the atoms and allowing more precise measurement of their transition frequency. The cesium atoms are launched upward in a fountain-like trajectory through a microwave cavity, and the interrogation of the atoms as they rise and fall through the cavity allows for an extremely long interaction time, which in turn improves the precision of the frequency measurement. Even more precise than cesium fountain clocks are the optical lattice clocks that have been developed over the past 2 decades. These clocks use atoms such as strontium or terbium, which are trapped in a lattice formed by intersecting laser beams and interrogated using visible light rather than microwaves. Because visible light has a frequency roughly 100,000 times higher than the microwave radiation used in cesium clocks, optical lattice clocks can divide time into correspondingly finer intervals, enabling measurements of even greater precision. The best optical lattice clocks currently in operation achieve accuracies of approximately 1 second in 15 billion years, which is roughly equal to the estimated age of the universe. At this level of precision, the clocks are sensitive to the effects of general relativity, running measurably faster or slower depending on their altitude above the Earth's surface, in accordance with Einstein's prediction that time passes more slowly in stronger gravitational fields. The practical applications of ultra-precise atomic clocks extend far beyond the mere telling of time. The global positioning system, which has become an indispensable tool for navigation, surveying, and a vast range of commercial and scientific applications, relies on a constellation of satellites, each carrying multiple atomic clocks. The GPS system determines the position of a receiver on the Earth's surface by measuring the time delay of signals transmitted from at least 4 satellites. Because the speed of electromagnetic radiation is approximately 299,792,458 meters per second, an error of just 1 nanosecond, 1 billionth of a second, in the time measurement would translate into a position error of approximately 30 centimeters. The atomic clocks aboard GPS satellites are accurate to within a few nanoseconds per day, enabling position determinations with a typical accuracy of a few meters for civilian users and considerably better for military and specialized applications. The relationship between timekeeping and the fundamental structure of the physical universe has been a subject of deep and sustained inquiry since the early 20th century. When Albert Einstein's theories of special and general relativity revealed that time is not the absolute, uniform, and universal quantity that it had been assumed to be since the days of Isaac Newton. In Newton's framework, time flowed at the same rate everywhere and for everyone, providing a fixed and immutable backdrop against which the events of the physical world unfolded. Einstein showed that this intuitive picture was fundamentally incorrect, and that the rate at which time passes depends on the relative velocity of the observer and on the strength of the gravitational field in which the observer is situated. The special theory of relativity, published by Einstein in 1905, demonstrated that time passes more slowly for an object in motion relative to a stationary observer, a phenomenon known as time dilation. The magnitude of this effect is negligible at everyday speeds, but becomes significant as the speed of the object approaches the speed of light. At 90% of the speed of light, time passes approximately 2.3 times more slowly for the moving object than for the stationary observer. At 99% of the speed of light, the factor increases to approximately 7.1, and at 99.9%, it reaches approximately 22.4. These predictions, counterintuitive as they may seem, have been confirmed by numerous experiments, including measurements of the lifetimes of unstable subatomic particles traveling at high speeds and direct comparisons of atomic clocks carried aboard aircraft with identical clocks remaining on the ground. The general theory of relativity, published by Einstein in 1915, extended these ideas to include the effects of gravity. According to general relativity, time passes more slowly in regions of stronger gravitational field. This gravitational time dilation means that a clock at the surface of the Earth, where the gravitational field is relatively strong, runs slightly slower than an identical clock at a higher altitude, where the gravitational field is weaker. The magnitude of this effect near the surface of the Earth is approximately 1 part in 10 to the 16th power per meter of altitude, which corresponds to a time difference of roughly 45 microseconds per day between a clock at sea level and a clock in orbit at an altitude of 20,200 kilometers, the orbital altitude of GPS satellites. The GPS system provides a striking practical demonstration of the effects predicted by both special and general relativity. The atomic clocks aboard GPS satellites are affected by two competing relativistic effects. The gravitational time dilation predicted by general relativity causes the satellite clocks to run faster than identical clocks on the ground, because the satellites are in a region of weaker gravitational field. The velocity-dependent time dilation predicted by special relativity causes the satellite clocks to run slower, because the satellites are moving at approximately 3.87 kilometers per second relative to the Earth's surface. The gravitational effect is larger, amounting to approximately 45.9 microseconds per day of faster running, while the velocity effect amounts to approximately 7.2 microseconds per day of slower running. The net effect is that the satellite clocks run faster than ground clocks by approximately 38.7 microseconds per day. If this relativistic correction were not applied, the position errors in the GPS system would accumulate at a rate of approximately 11.4 kilometers per day, rendering the system completely useless for navigation within a matter of hours. The history of timekeeping is also, in a very real sense, the history of standardization and international cooperation. The establishment of Coordinated Universal Time, known by the abbreviation UTC from the French Temps Universal Cordon, represents one of the most complex and carefully maintained systems of international coordination in existence. UTC is maintained by the Bureau International des Poids et Mesures, located in Sèvres, France, which combines the readings of approximately 450 atomic clocks housed in more than 80 national laboratories around the world to produce a weighted average that serves as the international standard of time. UTC differs from the purely astronomical timescale, known as UT1, which is based on the actual rotation of the Earth. Because the Earth's rotation is gradually slowing due to tidal interactions with the Moon, the length of the mean solar day is increasing by approximately 2.3 milliseconds per century. Over time, this gradual slowing causes UTC, which is based on the extremely stable frequency of cesium atomic clocks, to drift ahead of UT1. To keep UTC within 0.9 seconds of UT1, leap seconds are occasionally inserted into the UTC timescale. A leap second is an additional second added to the last minute of either June 30th or December 31st, resulting in a minute that is 61 seconds long rather than the usual 60. Since the practice of inserting leap seconds began in 1972, a total of 27 leap seconds have been added, the most recent being on December 31st, 2016. The practice of inserting leap seconds has proven to be surprisingly controversial, particularly in the age of digital technology. Computer systems and telecommunications networks, which rely on precise time synchronization, can experience difficulties when a leap second is inserted, because many software systems are not designed to handle a minute containing 61 seconds. Notable disruptions have occurred following leap second insertions, including problems affecting airline reservation systems, internet services, and even the Linux operating system kernel. As a result, there has been ongoing discussion within the international standards community about whether to abolish the leap second and allow UTC to drift freely from UT1, a change that would not become significant for hundreds of years, but which raises questions about the fundamental relationship between civil time and the astronomical cycles that have governed human timekeeping for millennia. The measurement of time at the smallest scales presents its own set of fascinating challenges. In the realm of particle physics and quantum mechanics, events occur on timescales that are almost inconceivably brief. The lifetime of a W boson, one of the carrier particles of the weak nuclear force, is approximately 3 times 10 to the negative 20th power seconds, or 300 yoctoseconds. The time required for light to cross the diameter of a proton is approximately 3 times 10 to the negative 24th power seconds. At these scales, the very concept of a sharp, well-defined moment in time begins to break down. And the quantum mechanical uncertainty principle places fundamental limits on the precision with which both the time and the energy of an event can be simultaneously known. At the other extreme of the temporal scale, the measurement of cosmological time, the age of the universe, and the duration of geological and astronomical processes has been one of the great achievements of modern science. The current best estimate of the age of the universe, based on observations of the cosmic microwave background radiation by the Planck satellite and other instruments, is approximately 13.787 billion years, with an uncertainty of approximately 20 million years. The age of the Earth, determined primarily through the radiometric dating of meteorites and the oldest known terrestrial rocks, is approximately 4.54 billion years, with an uncertainty of approximately 50 million years. The oldest known fossils of single-celled organisms date to approximately 3.5 billion years ago, while the oldest fossils of multicellular organisms date to approximately 600 million years ago. The methods used to measure these vast spans of geological and cosmological time are themselves worthy of detailed examination. Radiometric dating, which is the most widely used technique for determining the ages of rocks and minerals, relies on the decay of naturally occurring radioactive isotopes. The principle is straightforward. Certain isotopes, such as uranium-238, potassium-40, and carbon-14, are unstable and decay spontaneously into other elements at rates that are precisely known and are unaffected by external conditions such as temperature, pressure, or chemical environment. By measuring the ratio of the parent isotope to its decay product in a rock or mineral sample, and knowing the rate of decay, the age of the sample can be calculated. The half-life of uranium-238, which decays through a long chain of intermediate products to lead-206, is approximately 4.468 billion years. The half-life of potassium-40, which decays to argon-40, is approximately 1.248 billion years. The half-life of carbon-14, which decays to nitrogen-14, is approximately 5,730 years. The vastly different half-lives of these isotopes make them suitable for dating materials of vastly different ages. Carbon-14 dating is useful for organic materials up to approximately 50,000 years old, while uranium lead dating can be applied to rocks billions of years old. The precision of radiometric dating varies depending on the isotope and the quality of the sample, but uncertainties of less than 1% are routinely achieved for well-preserved samples. The measurement of time, from the earliest sundials and water clocks to the latest optical lattice clocks and gravitational wave detectors, represents one of the most sustained and successful intellectual enterprises in human history. Each advance in timekeeping technology has not only improved the accuracy with which time can be measured, but has also deepened our understanding of the nature of time itself. The sundial revealed the regularity of the Earth's rotation. The pendulum clock enabled the precise measurement of gravitational acceleration. The marine chronometer solved the problem of longitude and opened the oceans to safe navigation. And the atomic clock has confirmed the predictions of relativity and enabled technologies, such as GPS, that would have been unimaginable to earlier generations. The history of timekeeping is, in this sense, a history of humanity's relationship with one of the most fundamental and mysterious aspects of the physical universe, and the story is very far from over. The ongoing refinement of timekeeping technology continues to push the boundaries of what is measurable and what is knowable. Proposals have been made for nuclear clocks, which would use transitions in atomic nuclei rather than in atomic electron shells as their frequency reference. The thorium-229 nucleus possesses an exceptionally low-energy nuclear isomer transition with an energy of approximately 8.28 electron volts, corresponding to a frequency in the vacuum ultraviolet range. A clock based on this transition could potentially achieve an accuracy of 1 part in 10 to the 19th power, roughly 1,000 times better than the best current optical lattice clocks. Such a clock would be sensitive to variations in the fundamental constants of nature, including the fine structure constant and the ratio of the strong interaction to the electromagnetic interaction, and could therefore serve as a tool for testing some of the most basic predictions of modern physics. The story of timekeeping, from the shadow of a stick falling across the sand of an ancient Egyptian courtyard to the quantum mechanical oscillations of atoms cooled to within a fraction of a degree of absolute zero, is a story of relentless human curiosity and ingenuity applied to one of the most elemental aspects of existence. Time, which seems so simple and so obvious in our daily experience, has proven to be one of the most profound and elusive concepts in all of science, and the instruments we have built to measure it reflect, in their increasing subtlety and precision, the depth and complexity of the phenomenon they seek to capture. The ticking of a clock, whether it is the drip of water from a clepsydra, the swing of a pendulum, the vibration of a quartz crystal, or the transition of a cesium atom, is in each case a small window into the fundamental structure of the physical world, and the patient act of counting those ticks, second by second, minute by minute, hour by hour, is one of the most characteristically human endeavors there is. The evolution of timekeeping in the domestic sphere proceeded along a path that was largely separate from the development of precision instruments for scientific and navigational purposes, though the two trajectories inevitably influenced each other in numerous ways. The household clock, which first appeared in the homes of wealthy Europeans during the 15th century, underwent a gradual transformation from a rare and expensive curiosity into a ubiquitous fixture of daily life. The earliest domestic clocks were weight-driven wall clocks, often fitted with elaborate cases of carved wood or cast iron, and they were prized as much for their decorative value as for their timekeeping function. The long case clock, more commonly known as the grandfather clock, emerged in the late 17th century as a direct consequence of the invention of the pendulum clock. The long, narrow case was necessary to house the pendulum, which in the most common designs was approximately 1 meter in length and beat with a period of 2 seconds, and to accommodate the weights that drove the clock mechanism. The earliest long case clocks were produced in London in the 1660s and 1670s, and the form quickly spread to the Netherlands, Germany, and eventually to the American colonies. The cases of long case clocks became increasingly elaborate over the course of the 18th century, with fine examples featuring veneers of walnut, mahogany, or rosewood, inlaid with marquetry or lacquered in the Chinese style. The cuckoo clock, which is perhaps the most widely recognized form of domestic timepiece, has its origins in the Black Forest region of southwestern Germany, though the precise date and circumstances of its invention are matters of some uncertainty. The earliest written reference to a cuckoo clock dates to 1629, in a description by the Augsburg nobleman Philipp Hainhofer, but the widespread production of cuckoo clocks in the Black Forest appears to have begun in the mid-18th century. The mechanism that produces the characteristic two-note call of the cuckoo consists of 2 small bellows connected to 2 pipes of different lengths, which are activated by a system of levers and wires triggered by the clock's striking train. The lower note is typically tuned to approximately 440 Hz, the standard concert pitch of A above middle C, while the upper note is a minor third higher, at approximately 523 Hz. The mantel clock, designed to sit upon a shelf or mantelpiece, became popular in France during the reign of Louis XIV in the late 17th century and rapidly spread throughout Europe. French mantel clocks of the 18th century were often housed in cases of extraordinary artistic merit, featuring gilded bronze or ormolu, fashioned into elaborate allegorical and mythological scenes. The clock movement itself was frequently of secondary importance to the case, and it was not uncommon for the finest Parisian casemakers to charge considerably more for the case than the clockmaker charged for the movement. The styles of mantel clock cases followed the broader trends of decorative art, progressing from the Baroque through the Rococo to the Neoclassical, and each period produced its characteristic forms and motifs. The development of the pocket watch over the course of the 17th, 18th, and 19th centuries represents one of the most sustained exercises in precision miniaturization in the history of technology. The earliest pocket watches, produced in the 16th century, were thick, bulky devices with a single hour hand and no crystal or glass over the dial. The introduction of the balance spring, independently developed by Christian Huygens and Robert Hooke in the 1670s, dramatically improved the accuracy of watches and made it practical to add a minute hand to the dial. The balance spring, a thin spiral of metal attached at one end to the balance wheel and at the other to the watch frame, provided a restoring force that caused the balance wheel to oscillate with a regular period, serving the same function in a watch that the pendulum served in a clock. The accuracy of pocket watches continued to improve throughout the 18th and 19th centuries, driven by a series of incremental innovations in escapement design, jewelling, temperature compensation, and manufacturing technique. The lever escapement, invented by Thomas Mudge in approximately 1755, became the standard escapement for pocket watches and wristwatches, and it remains in use in mechanical watches to this day. The introduction of synthetic jewel bearings, typically made of ruby or sapphire, reduced friction at the pivot points of the gear train and improved both the accuracy and the longevity of the movement. The most refined pocket watches of the 19th century, produced by firms such as Abraham Louis Breguet in Paris, John Arnold and Thomas Earnshaw in London, and later by Patek Philippe and Vacheron Constantin in Geneva, achieved accuracies of a few seconds per day and were regarded as instruments of scientific precision, as well as objects of personal adornment. The transition from the pocket watch to the wristwatch occurred gradually during the late 19th and early 20th centuries. Wristwatches were initially regarded as a feminine accessory, and the idea of strapping a timepiece to the wrist was considered effeminate by many men. This attitude changed during World War I, when soldiers found wristwatches far more practical than pocket watches in the conditions of trench warfare. The need to coordinate artillery bombardments, infantry advances, and other military operations required quick and easy access to the time, and fumbling with a pocket watch while under fire was both impractical and dangerous. By the end of the war, the wristwatch had become firmly established as a masculine accessory, and the pocket watch began its long decline into obsolescence. The industrialization of watchmaking, which began in the United States in the mid-19th century and later spread to Switzerland and other countries, transformed the watch from a handmade luxury item into a mass-produced consumer good. The American Watch Company, founded in Waltham, Massachusetts, in 1850, was among the first to apply the principles of interchangeable parts and machine production to watchmaking. By the 1870s, the Waltham factory was producing approximately 100,000 watches per year, each one assembled from machine-made components that were sufficiently uniform to be interchangeable. This was a revolutionary departure from the traditional European method of watchmaking, in which each watch was individually crafted by a skilled artisan who made and fitted each component by hand. The Swiss watch industry, which had dominated the luxury end of the market for over a century, initially resisted the American approach to mass production, viewing it as a threat to the traditional craftsmanship that was the foundation of Swiss watchmaking's reputation. However, by the early 20th century, the Swiss industry had adopted many of the American techniques while continuing to maintain its expertise in high-end hand finishing and complication work. The result was an industry that was capable of producing watches at every level of the market, from inexpensive pin lever movements for the mass market to elaborate grand complications incorporating perpetual calendars, minute repeaters, and tourbillons for the most discerning collectors. The electric clock, which used an electromagnet to maintain the oscillation of a pendulum or balance wheel, was developed in the mid-19th century. Alexander Bain, a Scottish clockmaker and inventor, is generally credited with the first electric clock, which he patented in 1841. Bain's clock used an electromagnetic impulse to sustain the swing of a pendulum, drawing its power from a simple earth battery consisting of zinc and copper plates buried in moist ground. Later electric clocks drew their power from dry cell batteries or from the alternating current mains supply, using the frequency of the alternating current, which was maintained at a highly stable 50 or 60 Hz by the electricity generating authorities as a time base. The synchronous electric clock, which derived its timekeeping accuracy directly from the frequency of the alternating current supply, became the standard household timepiece in many countries from the 1930s onward. These clocks were inexpensive, reliable, and, because the frequency of the power supply was carefully regulated, quite accurate. The principle was simple. A small synchronous motor, driven by the alternating current supply, turned at a rate that was directly proportional to the supply frequency. A gear train then reduced this rotation to the appropriate rates to drive the hour, minute, and second hands. The accuracy of a synchronous electric clock was determined entirely by the accuracy of the power supply frequency, which was typically maintained to within a few parts per million by the generating authorities. The digital clock, which displays the time in numerical form rather than by the position of hands on a dial, became widely available in the 1970s following the development of inexpensive light-emitting diode and liquid crystal display technologies. The first digital wristwatches, such as the Hamilton Pulsar, introduced in 1972, used red LED displays that consumed considerable power and could only be read by pressing a button to illuminate the display. The subsequent adoption of liquid crystal displays, which required far less power and could be continuously visible, made digital watches practical for everyday use. By the early 1980s, digital watches had become extremely inexpensive, with basic models available for a few dollars, and they had largely displaced mechanical and analog quartz watches at the lower end of the market. The concept of time zones and the standardization of civil time across large geographical areas has continued to evolve since the initial establishment of the time zone system in the 1880s. The total number of time zones currently in use around the world is considerably larger than the 24 that would result from a simple division of the globe into 15-degree zones. Many countries have adopted time offsets that differ from coordinated universal time by half-hour or even quarter-hour increments. India, for example, uses a single time zone, Indian Standard Time, which is offset from UTC by 5 hours and 30 minutes. Nepal uses a time offset of 5 hours and 45 minutes, and the Chatham Islands of New Zealand use an offset of 12 hours and 45 minutes. In total, there are currently approximately 40 distinct time offsets in use around the world, a number that is further complicated by the practice of daylight saving time, which is observed in some countries but not in others, and which shifts the local time by 1 hour for part of the year. Daylight saving time, the practice of advancing clocks by 1 hour during the summer months to make better use of daylight in the evening, was first proposed by Benjamin Franklin in 1784, though his suggestion was made somewhat in jest. The idea was revived more seriously in the early 20th century, and Germany became the first country to implement daylight saving time on a national basis, doing so on April 30th, 1916, as a wartime measure to conserve coal. Other countries quickly followed, and daylight saving time was widely adopted during both World War I and World War II. After each war, the practice was abandoned by many countries, only to be reintroduced during subsequent energy crises. The effects of daylight saving time on energy consumption, health, and public safety have been the subject of considerable study and debate. Proponents argue that the practice reduces energy consumption by shifting an hour of daylight from the morning, when many people are still asleep, to the evening, when they are active and would otherwise need to use artificial lighting. Critics counter that any energy savings from reduced lighting are offset by increased use of air conditioning in the warmer evening hours, and that the disruption to sleep patterns caused by the biannual time change has measurable negative effects on health, including a documented increase in the incidence of heart attacks and automobile accidents in the days following the spring transition. Several studies have attempted to quantify the net effect of daylight saving time on energy consumption, with results ranging from modest savings of approximately 0.5% to no savings at all, or even a slight increase in energy use. The philosophical dimensions of timekeeping have occupied thinkers for as long as time itself has been measured, and the history of the philosophy of time runs parallel to, though often separate from, the history of the instruments used to measure it. St. Augustine of Hippo, writing in the 4th century CE, famously remarked in his Confessions that he knew what time was when no one asked him, but when he tried to explain it, he found that he did not know. This paradox, the gap between our intuitive experience of time and our ability to articulate what time actually is, has remained a central problem in philosophy for more than 1,600 years. The Newtonian conception of time, which dominated scientific and philosophical thinking from the late 17th century until the early 20th century, treated time as an absolute, mathematical quantity that flowed uniformly and independently of any external influence. Newton distinguished between what he called absolute time, which was true mathematical time and which flowed equably without relation to anything external, and relative time, which was the common, sensible, and apparent measure of duration by means of motion, such as the swing of a pendulum or the rotation of the earth. For Newton, the purpose of clocks was to approximate absolute time as closely as possible, and the history of timekeeping was, in this framework, a history of increasingly successful approximation. The Leibnizian alternative, proposed by Newton's contemporary and rival Gottfried Wilhelm Leibniz, held that time was not an independently existing entity, but rather a system of relations between events. In Leibniz's view, time was nothing more than the order of succession of events, and without events, there would be no time. This relational view of time, though it was largely eclipsed by the Newtonian absolute view for more than 2 centuries, found unexpected support in Einstein's theories of relativity, which showed that the rate at which time passes depends on the physical circumstances of the observer, a finding that is difficult to reconcile with the notion of an absolute, uniformly flowing time. The phenomenological tradition in philosophy, associated particularly with the work of Edmund Husserl and Martin Heidegger in the early 20th century, approached the question of time from the perspective of human experience rather than physical measurement. Husserl distinguished between objective time, the time measured by clocks and calendars, and the internal time consciousness through which we experience the flow of time as a continuous stream of present moments, each carrying within it a retention of the immediate past and a pretension, or anticipation, of the immediate future. Heidegger went further, arguing in his magnum opus Being and Time, published in 1927, that temporality was the fundamental structure of human existence itself, and that our relationship to time, our awareness of our own mortality, and our ability to project ourselves into the future through planning and anticipation, was what distinguished human beings from other entities in the world. The relationship between timekeeping and social organization has been a subject of considerable interest to historians and sociologists. The historian E. P. Thompson, in his influential 1967 essay titled Time, Work Discipline, and Industrial Capitalism, argued that the spread of clocks and watches in the 18th and 19th centuries was intimately connected with the rise of industrial capitalism and the transformation of labor from task-oriented work, in which the duration of a task was determined by the task itself, to time-oriented work, in which labor was measured and compensated by the hour. Thompson contended that the clock was not merely a neutral instrument for measuring time, but was an active agent of social discipline, imposing an external, abstract temporal framework on workers who had previously organized their labor according to natural rhythms and personal judgment. The standardization of time, which proceeded in tandem with the spread of the railway and the telegraph in the 19th century, had profound effects on the experience of daily life that went far beyond the practical requirements of transportation scheduling. The adoption of standard time zones meant that the time shown on the clock no longer corresponded precisely to the position of the sun in the sky, a disjunction that was psychologically significant even if practically unimportant. In a town situated at the western edge of a time zone, the sun might not reach its highest point until well past noon by the clock, while in a town at the eastern edge, solar noon might occur well before clock noon. This imposition of an arbitrary, standardized time over the natural, locally determined time of the sun represented a profound shift in humanity's relationship with the cosmic cycles that had governed timekeeping since its earliest beginnings. The 20th and 21st centuries have witnessed an ever-increasing precision in the measurement of time, accompanied by an ever-expanding range of applications that depend on that precision. The synchronization of financial markets, the coordination of telecommunications networks, the operation of power grids, the control of satellite navigation systems, and the functioning of the Internet all depend on precise and reliable timekeeping. The Network Time Protocol, developed by David Mills at the University of Delaware in 1985, enables computers connected to the Internet to synchronize their clocks to within a few milliseconds of coordinated universal time, and more recent protocols have achieved synchronization to within microseconds or even nanoseconds. The distribution of precise time signals has itself a long and interesting history. The Royal Observatory at Greenwich began providing a time signal service in 1833, using a time ball, a large, brightly painted ball mounted on a pole on the roof of the observatory, which was dropped at precisely 1 o'clock each afternoon. Ships in the Thames and in the nearby docks could observe the falling ball and set their chronometers accordingly. The time ball at Greenwich continued to drop daily until 1936 and is still dropped today as a tourist attraction, though it no longer serves any practical timekeeping purpose. The telegraph enabled the distribution of time signals over much greater distances than could be achieved by visual means. The first regular telegraphic time signal service was established in Britain in 1852, when the Royal Observatory began transmitting a time signal over the telegraph network to various locations throughout the country. This service was soon supplemented by the speaking clock, a telephone service that announced the time on demand. The first speaking clock was introduced in France in 1933, and the British Post Office launched its own speaking clock service, known as the Timeline or TIM, on July 24, 1936. The original voice was that of Ethel Kane, a London telephone operator who had won a competition to select the most suitable voice for the service. The speaking clock remains in operation in several countries, though its use has declined substantially in the age of mobile phones and Internet-connected devices, each of which typically maintains its own accurately synchronized clock. Radio time signals provided another means of distributing accurate time to a wide audience. The first regular radio time signal service was established by the Eiffel Tower in Paris in 1910, and similar services were soon established by radio stations in other countries. The BBC began broadcasting the famous 6 pips time signal on February 5, 1924, and this signal, consisting of 6 short tones spaced 1 second apart with the last tone marking the exact hour, has been broadcast continuously ever since, making it one of the longest-running features in the history of broadcasting. The 6 pips signal is generated by the clock at the BBC's Broadcasting House in London, which is synchronized to the time signal from the National Physical Laboratory in Teddington. The measurement and regulation of time has become so deeply embedded in the infrastructure of modern civilization that it is difficult to imagine how daily life would function without it. From the alarm clock that wakes us in the morning to the atomic clocks that keep the internet running and the satellites in orbit, time and its measurement permeate every aspect of our existence. The history of timekeeping is, in this respect, not merely the history of a particular technology or set of instruments, but a history of one of the fundamental organizing principles of human society. A principle so pervasive and so deeply internalized that we are, for the most part, entirely unconscious of its operation. The ticking of the clock, whether audible or silent, mechanical or atomic, continues ceaselessly in the background of our lives, measuring out the seconds and minutes and hours with a patience and regularity that mirrors, however imperfectly, the steady and imperturbable flow of time itself. The calendar, which is perhaps the most visible and widely used product of humanity's effort to measure and organize time, has its own long and complex history that runs parallel to the history of clocks and watches. The fundamental challenge of calendar construction lies in the fact that the three principal astronomical cycles, the day, the month, and the year, are not commensurable, meaning that none of them divides evenly into any of the others. The mean solar day, defined as the average interval between successive passages of the sun across the local meridian, has a duration of approximately 24 hours, or more precisely 86,400 seconds. The synodic month, defined as the interval between successive new moons, has a mean duration of approximately 29.53059 days. The tropical year, defined as the interval between successive passages of the sun through the vernal equinox, has a mean duration of approximately 365.24219 days. Because 365.24219 is not an integer, and because 365.24219 divided by 29.53059 yields the irrational number 12.36827. It is impossible to construct a calendar that simultaneously maintains perfect alignment with both the solar year and the lunar month while using whole numbers of days. The earliest calendars were predominantly lunar, based on the easily observable cycle of the moon's phases. The lunar month of approximately 29.5 days provided a natural unit for organizing time, and 12 lunar months yielded a year of approximately 354 days, which was close enough to the solar year of 365.25 days to serve the needs of societies that did not depend heavily on agriculture. However, the discrepancy of approximately 11 days between the lunar year of 354 days and the solar year of 365.25 days meant that a purely lunar calendar would gradually drift out of alignment with the seasons, completing a full cycle of drift in approximately 33 years. This drift was unacceptable for agricultural societies, which needed a calendar that kept the planting and harvesting seasons in their proper places, and various methods of intercalation, the insertion of extra days or months, were devised to reconcile the lunar and solar cycles. The ancient Egyptians were among the first to adopt a solar calendar, abandoning the lunar month as the fundamental unit of time in favor of a year of 365 days divided into 12 months of 30 days each, plus 5 additional days, known as epagomenal days, at the end of the year. This calendar was in use by at least 2800 BC and possibly earlier. However, because the true length of the solar year is approximately 365.25 days rather than exactly 365 days, the Egyptian calendar drifted by 1 day every 4 years relative to the seasons, completing a full cycle of drift in approximately 1,460 years, a period known as the Sothic cycle because the Egyptians tracked the drift by observing the heliacal rising of the star Sirius, which they called Sopdet or Sothis. The Julian calendar, introduced by Julius Caesar in 46 BC on the advice of the Alexandrian astronomer Sosigenes, represented a significant improvement over the Egyptian calendar by incorporating a leap year every 4 years. This gave the Julian calendar an average year length of 365.25 days, which was much closer to the true length of the tropical year than the 365-day Egyptian year. The Julian calendar was widely adopted throughout the Roman Empire and remained in use in most of Europe for more than 16 centuries. However, the Julian calendar's average year length of 365.25 days was slightly too long, exceeding the true tropical year of 365.24219 days by approximately 0.0078 days, or about 11 minutes and 14 seconds. This small error accumulated over the centuries, causing the calendar to drift by approximately 1 day every 128 years. By the 16th century, the cumulative drift amounted to approximately 10 days, and the vernal equinox, which the Julian calendar placed on March 21st, was actually occurring on approximately March 11th. This discrepancy was of particular concern to the Christian Church, because the date of Easter was calculated with reference to the vernal equinox, and the drift of the equinox was causing Easter to occur at increasingly inappropriate times relative to the astronomical spring. Pope Gregory XIII addressed this problem in 1582 by issuing the papal bull Inter Gravissimas, which introduced the Gregorian calendar reform. The reform had 2 components. First, 10 days were dropped from October 1582, with October 4th being followed immediately by October 15th, to bring the calendar back into alignment with the astronomical seasons. Second, the leap year rule was modified so that century years, those divisible by 100, would not be leap years unless they were also divisible by 400. Thus, the years 1700, 1800, and 1900 were not leap years under the Gregorian calendar, but 2000 was. This modification reduced the average length of the calendar year from 365.25 days to 365.2425 days, which differs from the true tropical year by only 0.0003 days, or approximately 26 seconds. At this rate of drift, the Gregorian calendar will accumulate an error of 1 day in approximately 3,236 years. The adoption of the Gregorian calendar was by no means immediate or universal. Catholic countries, including Spain, Portugal, Italy, and France, adopted the new calendar in 1582 or shortly thereafter, but Protestant and Orthodox countries were reluctant to accept a reform promulgated by the Pope. The Protestant states of Germany did not adopt the Gregorian calendar until 1700. Britain and its colonies waited until 1752, and Russia did not make the change until 1918, following the Russian Revolution. Greece was the last European country to adopt the Gregorian calendar, doing so in 1923. The delay in adoption meant that for much of the 17th and 18th centuries, dates in different parts of Europe could differ by 10 or 11 days, a source of considerable confusion in international correspondence and commerce. The Islamic calendar, which is used throughout the Muslim world for religious purposes, is a purely lunar calendar consisting of 12 months of alternately 29 and 30 days, yielding a year of 354 or 355 days. Because no intercalation is employed, the Islamic calendar drifts relative to the seasons at a rate of approximately 10 or 11 days per year, completing a full cycle in approximately 33 lunar years, or approximately 32 solar years. This means that Islamic religious observances, such as the month of Ramadan, cycle through all seasons over the course of approximately 3 decades. The Hebrew calendar, used for Jewish religious purposes, is a lunisolar calendar that reconciles the lunar and solar cycles through a system of intercalation in which an additional month, known as Adar II, is inserted 7 times in every 19-year cycle. This 19-year cycle, known as the Metonic cycle after the Greek astronomer Meton, who described it in 432 BCE, is based on the observation that 235 synodic months are almost exactly equal to 19 tropical years. The difference between these two periods is only approximately 2 hours over the 19-year cycle, making the Metonic cycle an exceptionally accurate basis for lunisolar calendar construction. The Chinese calendar, which has been in continuous use for over 2,000 years, is also a lunisolar calendar, with months beginning at the new moon and an intercalary month inserted approximately every 3 years to maintain alignment with the solar year. The Chinese calendar incorporates a sexagenary cycle of 60 years, formed by the combination of 10 celestial stems and 12 terrestrial branches, the latter being associated with the familiar Chinese zodiac animals. This 60-year cycle has been used to number years since at least the 1st century BCE, and the current cycle, the 78th, began in 1984. The measurement of time on very short scales has applications in fields as diverse as photography, telecommunications, chemistry, and fundamental physics. The stroboscope, invented by the Belgian physicist Joseph Plateau in 1832, was one of the earliest instruments capable of capturing or analyzing events occurring on timescales of milliseconds. The electronic flash, developed in the 1930s by Harold Edgerton at the Massachusetts Institute of Technology, could produce flashes of light as brief as 1 microsecond, enabling the capture of high-speed photographs that revealed phenomena invisible to the unaided eye, such as the precise shape of a bullet in flight or the crown-like splash formed by a single drop of milk falling into a thin layer of milk. The development of mode-locked lasers in the 1960s and 1970s made it possible to generate pulses of light with durations measured in picoseconds, trillionths of a second. And subsequent refinements pushed pulse durations into the femtosecond regime, or quadrillionths of a second. A femtosecond is to a second as a second is to approximately 31.7 million years, a comparison that conveys some sense of the extraordinary brevity of these intervals. Femtosecond laser pulses have found important applications in chemistry, where they are used to observe and control the progress of chemical reactions on the timescale at which individual molecular bonds are formed and broken, a field known as femtochemistry, for which Ahmed Zewail received the Nobel Prize in Chemistry in 1999. More recently, the development of attosecond light pulses with durations of approximately 1 quintillionth of a second has opened a window into the dynamics of electrons within atoms, enabling the direct observation of processes such as the ionization of atoms by ultraviolet light and the tunneling of electrons through potential barriers. Pierre Agostini, Ferenc Krauss, and Lewilier were awarded the Nobel Prize in Physics in 2023 for their contributions to the development of attosecond science. The attosecond is currently the shortest time interval that can be directly measured, though theoretical considerations suggest that meaningful timescales extend down to the Planck time, approximately 5.39 times 10 to the negative 44th power seconds, which represents the time scale at which quantum gravitational effects are expected to become significant and at which the conventional notion of time as a smooth, continuous quantity may break down entirely. The history of timekeeping, considered in its full sweep from the earliest shadow clocks of ancient Egypt to the attosecond laser laboratories of the 21st century, reveals a progressive deepening of human understanding of one of the most fundamental aspects of physical reality. Each new timekeeping technology has not only provided a more accurate measure of duration, but has also posed new questions about the nature of time itself. The sundial raised questions about the relationship between time and the motion of celestial bodies. The pendulum clock raised questions about the relationship between time and gravity. The atomic clock raised questions about the relationship between time and the quantum mechanical properties of matter. And the ultra-precise optical clocks of the present day, sensitive as they are to the effects of general relativity, raise questions about the relationship between time and the very fabric of space-time. As the seconds continue to pass, each one now defined with extraordinary precision by the oscillations of a cesium atom, the story of timekeeping remains open and ongoing. Future developments may include the redefinition of the second in terms of optical transitions rather than microwave transitions, The deployment of networks of ultra-precise clocks for applications such as geodesy and gravitational wave detection, and perhaps, eventually, a deeper understanding of the nature of time itself, an understanding that may revise or even transcend the conceptions of time that have guided humanity's greatest thinkers from Augustine to Einstein and beyond. For now, the clocks continue to tick, the atoms continue to oscillate, and time, whatever it ultimately proves to be, continues its steady and silent passage through the universe. The influence of timekeeping on the arts and literature provides yet another dimension through which to appreciate the profound significance of humanity's effort to measure the passage of hours and days. The clock, as both a physical object and a metaphorical concept, has occupied a prominent place in Western art and literature for centuries. In painting, clocks and hourglasses frequently appear as symbols of mortality and the transience of earthly pleasures, a tradition known as vanitas that reached its fullest expression in Dutch still life painting of the 17th century. In these paintings, a clock or hourglass is typically placed alongside other symbols of impermanence, such as wilting flowers, rotting fruit, guttering candles, and human skulls, creating a contemplative tableau that invites the viewer to reflect upon the brevity of life and the inevitability of death. The literary treatment of time has been no less rich or varied. Marcel Proust's monumental novel In Search of Lost Time, published in 7 volumes between 1913 and 1927, is perhaps the most sustained and celebrated literary exploration of the nature of time, memory, and human consciousness. Proust distinguished between voluntary memory, the deliberate effort to recall past events, which he found to be inevitably incomplete and unsatisfying, and involuntary memory, the sudden, unbidden recollection of the past triggered by a sensory experience, such as the taste of a madeleine dipped in tea. For Proust, it was through involuntary memory that the true essence of the past could be recovered, and the entire arc of his novel can be understood as an attempt to transcend the destructive effects of time through the redemptive power of art and memory. The clock tower, as an architectural form, has been a prominent feature of the European cityscape since the late Middle Ages. The earliest public clock towers were associated with churches and cathedrals, reflecting the close connection between timekeeping and religious observance in medieval society. The clock tower of the Palazzo Vecchio in Florence, dating to the early 14th century, and the astronomical clock in the Old Town Square of Prague, installed in 1410, are among the most celebrated examples. These towers served not only as timekeepers, but also as symbols of civic pride and municipal authority. And the competition among cities to build the most impressive clock tower was a significant driver of innovation in both clockmaking and architecture. The tower clock at the Palace of Westminster in London, commonly known as Big Ben, though that name technically refers only to the largest of the 5 bells housed within the tower, is perhaps the most famous clock in the world. The tower was designed by Augustus Pugin and completed in 1859, and the clock mechanism was designed by Edmund Beckett Denison, later Lord Grimthorpe. The clock has 4 dials, each measuring 7 meters in diameter, and the minute hands are each 4.3 meters long. The timekeeping is regulated by a double 3-legged gravity escapement, an innovative design by Denison that isolates the pendulum from variations in the force transmitted by the clock's driving mechanism. The accuracy of the clock is maintained by the addition or removal of old penny coins from a tray near the top of the pendulum, each coin causing a change in the clock's rate of approximately 0.4 seconds per day. The development of time signals and their distribution through various media has created a network of temporal coordination that is now so seamless and so pervasive that it is largely invisible to those who depend upon it. The average person in the developed world encounters dozens of time displays each day, from the clock on their mobile phone to the timestamp on an email, from the departure boards at railway stations to the countdown timer on a microwave oven. Each of these displays is synchronized, directly or indirectly, with the atomic time standards maintained by national metrology institutes, creating a web of temporal agreement that spans the globe. The psychological experience of time, which is the subject of an extensive body of research in experimental psychology, is a fascinating counterpoint to the objective measurement of time by clocks and calendars. The subjective duration of a period of time can differ dramatically from its objectively measured duration, depending on a variety of factors including the level of attention devoted to the passage of time, the emotional state of the individual, the complexity and novelty of the events occurring during the period, and even the body temperature of the observer. Time appears to pass more slowly when one is bored, anxious, or in pain, and more quickly when one is engaged in an enjoyable or absorbing activity, a subjective distortion that has been documented in numerous experimental studies. The phenomenon of temporal illusions, in which the perceived duration of an event differs systematically from its actual duration, has been studied extensively by psychologists. The oddball effect, for example, is the observation that a novel or unexpected stimulus in a sequence of repeated stimuli is perceived as lasting longer than the repeated stimuli, even when all stimuli are of identical objective duration. This effect is thought to arise from the greater amount of neural processing devoted to the novel stimulus, which creates a richer memory representation and thereby gives rise to the subjective impression of greater duration. The filled duration illusion is another well-documented phenomenon, in which a time interval filled with events or stimuli is perceived as longer than an empty interval of the same objective duration. The relationship between age and the subjective experience of time has been a matter of common observation and folk wisdom for centuries, with older adults frequently reporting that time seems to pass more quickly than it did when they were young. Several explanations have been proposed for this phenomenon. The proportional theory suggests that each successive year constitutes a smaller fraction of one's total life experience and therefore seems subjectively shorter. The first year of life constitutes 100% of one's experience, while the 50th year constitutes only 2%. The novelty theory proposes that childhood and youth are filled with novel experiences that create rich and detailed memories, giving the subjective impression of long duration, while the routine repetition of adult life creates fewer distinctive memories, compressing the subjective sense of elapsed time. The biological theory suggests that changes in the rate of an internal neural clock, which is thought to slow with age, cause older adults to perceive external time as passing more quickly than it actually does. The cultural construction of time, the ways in which different societies conceptualize and organize temporal experience, varies considerably across the world. Western industrialized societies tend to conceive of time as a linear progression from past through present to future, with the future lying ahead and the past behind. This linear conception of time is so deeply embedded in Western culture that it is often assumed to be universal, but anthropological research has shown that many cultures conceptualize time in fundamentally different ways. The Aymara people of the Andes, for example, use spatial metaphors for time in which the past is in front, because it can be seen and known, while the future is behind, because it is unseen and unknown, a reversal of the Western convention. The Hopi language, according to the linguistic analyses of Benjamin Lee Whorf, which have been the subject of considerable debate, does not make the same sharp distinction between past, present, and future that is characteristic of Indo-European languages, suggesting a fundamentally different way of experiencing temporal reality. The concept of deep time, the vast stretches of geological and cosmological history that extend far beyond the scale of human experience, has been one of the most profound conceptual achievements of modern science. The realization that the Earth is not thousands, but billions of years old, and that the universe itself has existed for nearly 14 billion years, fundamentally altered humanity's sense of its own place in the temporal scheme of things. James Hutton, the Scottish geologist who is often regarded as the father of modern geology, wrote in 1788 that the geological record revealed no vestige of a beginning, no prospect of an end, a statement that captured the dizzying sense of temporal vastness that the study of rocks and fossils had begun to reveal. The measurement of deep time through radiometric dating and other techniques has provided a framework within which the entire history of the universe, the Earth, and life on Earth can be organized and understood. The geological timescale, which divides the history of the Earth into eons, eras, periods, epochs, and ages, is calibrated by radiometric dates and provides a common temporal reference for geologists, paleontologists, biologists, and other scientists. The boundaries between the major divisions of the geological time scale are typically marked by significant events in the history of life or of the Earth itself, such as mass extinctions, the appearance of new groups of organisms, or major changes in the composition of the atmosphere or oceans. The concept of cosmic time, the time scale of the universe as a whole, presents philosophical challenges that are even more profound than those posed by geological deep time. The Big Bang Theory, which is the prevailing cosmological model, holds that the universe began approximately 13.787 billion years ago in an extremely hot and dense state, and has been expanding and cooling ever since. The question of what, if anything, existed before the Big Bang is one that pushes the limits of both physics and philosophy. Some cosmological models suggest that time itself began with the Big Bang, meaning that the question of what came before is literally meaningless, much as the question of what lies north of the North Pole is meaningless. Other models propose that the Big Bang was not the beginning of time, but merely a transition from a prior phase of the universe's existence, and that time extends infinitely into the past as well as, potentially, into the future. The future of timekeeping is likely to be shaped by the same forces that have driven its development throughout human history: the desire for greater accuracy, the needs of navigation and communication, the requirements of scientific research, and the relentless human drive to understand the fundamental nature of reality. The development of quantum clocks, which exploit the quantum mechanical properties of entangled particles to achieve accuracies beyond the reach of current atomic clocks, is an active area of research. The potential deployment of clock networks for the detection of dark matter and the measurement of gravitational waves represents a new and exciting application of ultra-precise timekeeping. And the ongoing effort to understand the nature of time at the Planck scale, where quantum gravitational effects are expected to become dominant, may ultimately lead to a revolution in our understanding of time that is as profound as the revolution wrought by Einstein's theories of relativity in the early 20th century. The clock, in all its forms, from the shadow on a sundial to the oscillation of an atom, remains one of humanity's most characteristic and revealing creations. It is a tool of extraordinary practical utility, an object of aesthetic beauty and cultural significance, and a window into some of the deepest questions that human beings have ever asked. The steady tick of the clock, whether real or metaphorical, marks the passage of moments that will not come again, and the history of our efforts to measure those moments is, in a very real sense, the history of our struggle to comprehend the mysterious medium through which our lives unfold. As the hours pass and the centuries accumulate, the clocks tick on, patient and indifferent, counting out the seconds of a universe that is, by all current indications, very large and very old and, perhaps, very far from finished with its counting.